Hi, this is a story of the Soleq EVcort. It was an experimental electric vehicle produced from 1981 through 1994. Probably fewer than 100 were ever produced, so obviously it was not a commercial success. But the EVcort had several features that are common on EVs today but were quite innovative at the time, so it has a unique but little known place in EV history. The story begins with a small company in Cleveland called Electric Vehicle Associates. In the late 1970s, they performed a few hundred EV conversions on various vehicles, including the Ford Fairmont. For the motor controllers in these vehicles, they contracted with the Soleq Corporation of Chicago, a small electronics firm that made, among other things, inverters and battery chargers for off-grid solar installations. But in a twist that's oddly reminiscent of Tesla, they were also into aeronautics, where they made power supplies and other components for the electrical systems of airliners. The head engineer at Soleq was Shunjiro Ohba. He had a PhD in electrical engineering, and in 1979 he filed a patent describing a new kind of motor controller for electric vehicles. It was much more complex than existing controllers because it regulated the field and armature windings of a vehicle's brushed DC motor independently and automatically. It was essentially a computer that controlled the DC motor in much the way microprocessors control just about everything in a modern vehicle, but it used analog rather than digital circuitry. In 1981, Soleq again teamed up with Electric Vehicle Associates to create a vehicle based on Shunjiro Ohba's novel controller. It was an ambitious effort to produce the best EV possible with available technology, with little regard to the cost. All of the electronics were custom designed specifically for the vehicle and were assembled at Soleq under Ohba's direction. He contracted with General Electric to produce a special Sepex motor designed to work optimally with his controller. As a mechanical platform for the vehicle, Ohba chose the Escort, which was Ford Motor Company's new front-wheel drive compact, and he convinced Ford to provide engineless bodies into which the electric drivetrain and batteries could be fitted. EVA and Soleq called their new vehicle the EVcort, with the EV capitalized. I've been unable to find any record of exactly how many EVcorts were produced, but it's clear that the car's creators initially planned to manufacture hundreds of them for sale to the general public, with a goal of at least 300 vehicles in the first year. They sent out press releases and had brochures printed up that promoted the EVcort as a practical alternative to gasoline-powered cars. They claimed an average range of 60 miles and a top speed of 70 miles an hour, increasing to 100 miles at 30 miles an hour. Of course, that's pretty pathetic by today's standards, but it was quite impressive compared to other EVs of that era, almost all of which were relatively simple, improvised designs. An early press release for the EVcort gives a suggested base price of $16,465 before options. So let's see about $18,000 for a reasonably well-equipped model. That was 3 times the price of a 1981 gas Escort, which cost about $6,000. In inflated 2025 dollars, the EVcort would cost $60,000 today for a car that, even with new batteries and under ideal conditions, could only go 60 miles. So in the end, very few EVcorts were ever sold directly to consumers. Most, if not all of them, were bought by government laboratories, power companies, and other public institutions to be used as testing and demonstration vehicles. But before we continue with the history, let's look at some of the features of the 1981 EVcort. To illustrate, I'll be using my own 1988 model, which has the same basic design and may be the last EVcort still on the road. The heart of the EVcort was the special Sepex DC motor and the Soleq controller that powered it. Sepex stands for separately excited, which means the field and armature windings of the brushed DC motor are regulated independently, which is quite difficult to do effectively over the wide range of speeds and acceleration needed in a vehicle, and it requires a very sophisticated controller. But it does have some major advantages. It allows for stronger torque and better acceleration over a wider range of motor speeds with less shifting of gears. But perhaps more importantly, a Sepex motor can be easily adapted for regenerative braking, which few, if any, EVs had at that time. To understand why, we'll need a brief discussion of DC motors. There are 3 ways to wire a brushed DC motor. In a shunt configuration, the field windings of the motor are wired in parallel with the armature, so the field strength depends only on the voltage applied and is independent of motor speed. At low speeds, a shunt motor has plenty of torque, but as the armature starts spinning faster, it generates an opposing voltage called back EMF that's directly proportional to motor speed. The back EMF reduces the armature current, and as a result, the torque drops off rapidly and linearly to zero as the motor speed increases. That's ideal for situations where you want to keep a constant motor speed regardless of the load on the motor. But for a motor vehicle, you want strong torque over a wide range of motor speeds. So most early EVs use series wound DC motors with the field wired in series with the armature. In this case, as the speed increases, back EMF increases and armature current decreases, just as in a shunt motor. But since the field is wired in series with the armature, the field current, and thus the field strength, also decreases. That reduces back EMF, allowing current to flow through the armature even at high speeds. As a result, a series wound motor produces a usable level of torque over a much wider range of speeds than a shunt motor. And because the field is to some extent self-regulating, the torque can be controlled with a simple controller that regulates the voltage sent to the motor. But you could increase the torque at all speeds even further if you could arbitrarily regulate the voltage to the field and the voltage to the armature independently, as the EVcort did. In particular, at high motor speeds, you could sharply reduce the voltage and current in the field to reduce back EMF, then run maximum current and voltage through the armature for maximum torque. This is something you could never do with a series wound motor where the armature current is always the same as the field current. This graph from Ohba's original patent application compares the torque at various speeds for a shunt motor, a series wound motor, and the EVcort Sepex motor and controller. You can see that it produces more torque at all speeds, but especially at higher speeds than either a shunt or a series motor. That's due to the ability of the dual controller to arbitrarily reduce the field current by as much as a factor of 10 under conditions of heavy acceleration and high motor speed. As a result, the EVcort could accelerate from a standing start to over 45 miles an hour in second gear, so in city driving you'd never have to shift gears. Here's a front view of my 1988 EVcort where I've removed the controller, so you can see under the battery box there's the Sepex motor. As you can see, it's quite large. It's 17 inches long, 11 inches in diameter, pretty much fills the whole bottom of the engine bay. And over on this end we have the manual transmission, and in front of it there's the vacuum pump and the vacuum reservoir for the power brakes. And then there's a cooling fan for the motor. And down there are the connections for the field. And over on the other end, these big thick cables, of course, those are the connections for the armature. Like most modern DC power supplies, the EVcort controller regulated the voltage of both the field and the armature using pulse width modulation. A circuit called a chopper turns the supply voltage on and off rapidly, giving a series of pulses. A filter choke then smooths out the pulses to produce a relatively constant DC voltage. The output voltage is roughly proportional to the width or duration of the pulses. For example, if the circuit is in the on state 1/3 of the time, the output will be approximately 1/3 of the battery voltage, and so on. This method maximizes the efficiency by minimizing power dissipation within the controller. Modern pulse width regulators use frequencies of at least 50 kilohertz, meaning there are 50,000 pulses per second, but that requires high power, high speed MOSFETs, which weren't generally available when Ohba designed his controller. The EVcort controller instead used more primitive bipolar junction transistors and ran at just 400 Hz, 100 times slower than modern controllers. But 400 Hz is the same frequency used for the AC electrical systems of airplanes, which use 400 Hz because the systems can be designed with smaller, lighter electrical components than 60 Hz systems. Yet most standard household appliances designed for 60 Hz will still work on 400 Hz AC. So Ohba and his engineers would have been very familiar with 400 Hz circuits and components from their work with the airline systems. The EVcort ran at about 108 volts DC, and the controller had a maximum current of 400 amps, and so could deliver about 40 kilowatts of power to the motor, equivalent to about 55 horsepower. Again, that might seem pathetic by today's standards, but it's comparable to the 97 cubic inch gasoline Escort engine, which produced just 65 horsepower. But each little bipolar transistor could only handle a small fraction of that power, so the EVcort controller wired dozens of them in parallel. Here's an interior view of the controller from my 1988 EVcort, which has 100 power output transistors, each passing about 4 amps or 400 watts to the motor. They're arranged in 5 banks of 20 transistors each, all connected in parallel with copper bus bars and mounted on aluminum brackets to dissipate heat to a single massive heat sink. The field was controlled separately by this bank of 6 similar transistors, delivering up to 17 amps at about 90 volts to the field. Of course, all those transistors made the controller quite large. Here's the controller of my 1988 EVcort. It's mounted at the front of the vehicle, where the radiator would normally be. It's in a sealed aluminum enclosure. It's 2 feet wide, a foot tall, and 8 inches deep, all packed with electronic components. The entire front of the controller is one big heat sink to dissipate the heat from all those power transistors. Because of the low 400 Hz pulse frequency, large capacitors and a single large choke were needed to filter out the ripple and deliver smooth DC to the motor. And here's the choke of my EVcort. As you can see, it's also quite large, probably weighs at least 35 pounds, way more than the whole controller of any modern EV. But the choke is important for another innovative feature of the EVcort controller, which is regenerative braking, where the motor acts as a generator to recharge the batteries whenever the brake pedal is depressed. In a Sepex motor, the back EMF is proportional to both motor speed and field strength. So at high motor speed, you can get regen simply by increasing the field voltage to the point that the back EMF exceeds the battery voltage. And that's exactly what the EVcort controller did, though of course in a very well-regulated manner. But once the motor slows down, at some point EMF drops below battery voltage, even at maximum field strength. Therefore, some EVcort controllers employed what Soleq called an up chopper, and what today we call a boost converter. A separate bank of transistors with a separate driver signal shorts the output of the motor directly through the filter choke with each pulse, building up a magnetic field in the choke. When the pulse driver turns the transistor off, the field collapses, maintaining the current flow and generating a higher voltage capable of recharging the battery. This arrangement provided up to 200 amps or 20 kilowatts of braking and recharging, and allowed regeneration even at very low speeds. My own 1988 controller has regen, but not a regen chopper, so perhaps only later EVcorts had this feature. To engage regeneration, the brake pedal was linked by a cable to a potentiometer that regulated both the field and the regen chopper. Depressing the brake pedal beyond the maximum regen engaged the standard vacuum-powered front disc and rear drum brakes, with vacuum provided by a 12-volt vacuum pump and reservoir. Regenerative braking was said to increase the EVcort's range by perhaps 2 to 8%, depending on conditions. The EVcort's battery pack consisted of 18 6-volt deep-cycle lead-acid batteries, like those typically used in golf carts and forklifts, wired in series for a nominal 108 volts. 11 were mounted in the rear in place of the gas tank and spare tire, with the top of the battery box rising about 6 inches above the original floor of the cargo area. The other 7 batteries were mounted in the engine compartment on top of the motor. 3 small fans provided ventilation to prevent the buildup of hydrogen gas during charging. While most EVs of the period had a large, separately charged, marine-style 12-volt battery for lights and other accessories, the EVcort had just a small 12-volt motorcycle battery, augmented with a DC to DC converter. The converter was basically an isolating 400 Hz switch mode power supply that took power from the 108-volt traction battery and produced up to 500 watts of regulated 14-volt DC, regardless of accessory load or the main battery state of charge. This was a major improvement, providing a much more stable and reliable source of accessory voltage than having a large 12-volt battery. Remarkably, most, if not all, EVcorts also had air conditioning. Its dual compressors, probably repurposed from a household window air conditioner, ran on 120-volt, 60-cycle AC power that was provided by a 20-amp, 2.5 kilowatt inverter. The inverter, with its own huge heatsink, was almost as large as the main controller and was mounted under the rear seats just in front of the back wheels. The condenser was mounted behind it under the rear battery box with 5 small fans to provide airflow. For heating the cabin in cold weather, a small gasoline-fired heater and half-gallon gas tank was added, which might seem an anomaly in an electric-powered vehicle, but using battery power for heating would have dramatically reduced the EVcort's range in cold weather, when range was already reduced due to the poor low-temperature performance of the batteries. The EVcort's onboard battery charger was mounted next to the rear battery box behind the left rear wheel. It operated on standard 120-volt AC power at up to 30 amperes or 3.5 kilowatts, but could also be set to draw 16 or 20 amps to accommodate standard household outlets. At 16 amps, a full charge from empty would require about 14 hours. Charging at 30 amps would take only 8 hours, but required a special high current outlet plug and cable. The charger had a complex profile, charging at the preset fixed current until it reached a set EOC, or end of charge voltage, sufficient to gas off some hydrogen and desulfate the electrolyte. The EOC was adjustable, but was automatically compensated for battery temperature. After about an hour at EOC, the voltage would drop to a slightly lower float voltage that was maintained indefinitely, periodically switching back to the EOC in order to top off the charge. This profile minimized the accumulation of lead sulfate precipitate, the main cause of battery degradation. A residential electric meter was mounted just inside the tailgate to record power consumption during charging. In 1988, the U.S. Department of Energy launched its Site Operator program, whereby it would underwrite the purchase of electric vehicles for testing purposes. The EVs were given to institutions such as electric utilities, universities, and research laboratories on condition that the use and performance of the EVs be documented. The vehicles came from a variety of manufacturers, and EVA and Soleq created a second batch of EVcorts for this program, again using the 1988 Ford Escort as a base. My own 1988 EVcort was one of several owned by the Sandia Laboratory in New Mexico, one of the U.S. national labs supported by the Department of Energy. These cars had the same basic design as in 1981, but the gasoline heater was replaced by a 2 kilowatt electric resistance heater that ran directly on 108-volt DC power from the traction battery. To minimize consumption of battery power during vehicle operation, the heater could be set to pre-warm the cabin using AC power from the charging cable once the batteries were fully charged. Similarly, in hot weather, the cabin could be pre-cooled by running the air conditioner directly on plug-in 120-volt AC power. The temperature set point was adjusted by a thermostat mounted behind the glove compartment. In general, the EVcorts performed well in the site operator field tests, receiving praise for their reliability and efficiency, although with some complaints of poor acceleration. A third and final batch of EVcorts was built in 1992 to 94, again at the behest of the Department of Energy. By that time, Soleq had acquired all the intellectual property rights from EVA and fully taken over production of vehicles, and the Ford Escort was in its second generation with a more rounded and less boxy styling. The controller still had the same basic design, and even though more efficient and more durable high-power MOSFETs were now available, Soleq kept to its practice of using dozens of parallel bipolar transistors for the power circuits. The pulse width modulation frequency was doubled from 400 to 800 Hz, replacing the huge 400 Hz choke with two much smaller ones. The controller of these later EVcorts also had a separate 60 transistor regen chopper, which greatly improved the effectiveness of the regenerative braking, allowing it to function even at very low speeds and bring the vehicle almost to a complete stop without engaging the mechanical brake. In addition, the basic flooded lead-acid batteries were replaced by Sonnenschein sealed lead-acid gel cells from Germany. The gel cells required no maintenance and had lower internal resistance, which improved the EVcorts' acceleration. Soleq claimed that they would have an average 6-year lifespan, about 2 years longer than the old flooded cells. But the gel cells were also more susceptible to damage from overcharging and were larger, heavier, and much more expensive, further boosting the cost of production. Two 1992 EVcorts were built for Kansas State University at a price of $58,000 each, which in 2025 dollars would be $130,000 each. And despite the improvements over the original design, by this time the EVcorts DC drivetrain was essentially obsolete, having been superseded by vehicles with AC motors such as the Soleq Force. High-power, high-speed MOSFET transistors developed in the 1980s facilitated variable frequency three-phase inverters that could drive brushless AC induction motors or permanent magnet synchronous motors, which were smaller, more efficient, and could more easily accommodate regenerative braking. The owner's manual for the 1992 EVcort describes it as a battery testing platform, indicating that all plans for commercial production as a consumer vehicle had long been abandoned. In fact, the manual specifically ruled out any production of EVcorts for sale to individuals and directed institutional owners to scrap the vehicles upon completion of testing. Nevertheless, a few were instead sold to hobbyists, and so finally came to be used as daily drivers, as the car's creators originally intended. I don't know how many EVcorts survive, but I suspect it's in the single digits. My own EVcort is still registered and licensed, but now the batteries are lithium, and most of the electronics have been replaced with modern components. Even today, half a century later, it's heartbreaking to read the promotional materials for the original EVcorts and appreciate the high hopes Shunjiro Ohba and Soleq had for the car in 1981, and the long hours Soleq technicians must have spent hand-wiring all those hundreds of transistors. To some extent, the EVcort was a victim of its own high ambitions to be a perfect electric vehicle. Instead of using standard off-the-shelf products, almost everything, including the motor, was specially designed and custom fabricated, with a view toward optimum integration and performance, with almost total disregard for the cost. And the inclusion of air conditioning, which added 200 pounds to a vehicle already weighed down with half a ton of batteries, seems particularly extravagant. But the biggest problem was the battery. Despite all its innovations, the 1981 EVcort was using basically the same flooded lead-acid cells that powered the Baker Electrics of 1899. They were heavy and dirty, required constant maintenance, performed poorly in cold weather, and lasted only a few years at most. Soleq engineers went to extraordinary lengths to squeeze the maximum range and lifespan from the batteries, and to make their EVcort as convenient and comfortable as possible. But it wasn't nearly enough, and in fact, widespread use of EVs was never a serious prospect as long as they relied on lead batteries. Still, the EVcort and similar vehicles showed what was possible and helped keep the dream of electric transportation alive until better batteries came along. Thanks for watching.